There's one other aspect of alternating series that makes them really nice to work with. And so we've already talked about how when you have an infinite series, it's very difficult to come up with the exact value of the series, and often it's very difficult just to approximate what that value would be. However, for alternating series, it turns out that it's very easy to approximate the true value of the series when it switches back and forth signs. And so we could draw a picture to see what's going on, and this picture is exactly the same idea as what we saw before with the partial sums, where I have S1, S2, S3, S4, S5, and so on. And so you can tell from this picture that the limiting value of this series as n goes to infinity has to be somewhere in between all of these dots. And so if I want to look at the error of an individual partial sum, or in other words, I want to guess how close is my partial sum, or the sum of the first 10 things, for example, to the final value of the series, then all I have to do is just see how close it is to the green line here, which is the true limiting value. And you can see, again, that each time to go in between, for example, S1 and S2, all I have to do is add in B2, which was the second term in my sequence. And then again, I would add in B3 to get to S3, and then I'd subtract off B4 to get to S4, and so on. But you can see that every single time I add in a new value, it crosses over the true value of the series as a whole. And so that indicates that the error in a partial sum is always less than the next term in the sum. And that's just because the arrows that I'm drawing are always longer than the distance from the dot to the green line. And since the arrows are always longer, that's the same as saying the next term is always bigger than the error. Again, this is only true for alternating series, and that makes it really easy to work with them. As an example, let's see how we could estimate this sum, minus 1 to the n plus 1 over n squared, to within 1 decimal place. So as a reminder, to within 1 decimal place, that's the same as saying within 1/10, because 1/10 is just equal to 0.1. And so as long as we're within 0.1, then we're within 1 decimal place. And so the idea for this is very simple. All I want to do is start writing out the terms in this series. And so if I plug in n equals 1, then I'm going to get minus 1 squared over 1, or in other words, just 1. If I plug in n equals 2, now the top is going to be a minus 1, and the bottom is going to be a 4. If I plug in n equals 3, then I get 1 over 9. If I plug in n equals 4, I get 1 over 16, and so on. And so we can already see here that this term is less than 1/10. And so that means that this partial sum is already close enough. And so this right here, the first 3 terms, are already a good enough estimate. And this is within 1/16 of the true value of the series. And so in general, all you have to do to estimate an alternating series to the precision that you want is just keep on writing out terms until you get the precision that you want. And then if you just sum up everything before that, that's your estimate.